title there. He's currently also the co-director of the NEES-funded Center of Excellence for risk-based community resilience.
All right, well, thank you, and thank you very much for having me and giving me the opportunity to share some experiences with the center, but also, you know, a number of tests that we did over the years here at UC San Diego. So community resilience, I was asked to speak today about community resilience. I'm going to show kind of a more you know, some testing, but then also get into the other components, which are less about buildings. And I think, you know, you heard Dr. Joy Poschke talk about, you know, a lot of things that NSF doesn't fund. And, you know, I think to some of us, sometimes that's news. I think most of us knew of the fire, but one thing they do fund is they do fund interdisciplinary research and community resilience. You'll hear my argument that it's in fact an interdisciplinary endeavor, and so I would encourage you to consider that, even if you're you know, a pure structural engineer, or you feel like a pure structural engineer. The opportunities, you don't have to do the social science research or the economics. There's people that can do that, and they can do it with you. So first, let me start with something that we're all familiar with. Some of you probably even are still paying back student loans. This is a different, it's the same Stafford Act, but it's the same Stafford, Robert Stafford. But this is 1974. The Disaster Relief Act was created by Nixon, and then Carter moved that forward with an executive order, and then finally, in 1988, Congress enacted the Stafford Act, and the intent was that local and state governments can develop disaster preparedness plans. So then, you know, switch gears a little bit. So we're thinking, you know, what's the purpose of having physical infrastructure? Well, the purpose of having physical infrastructure, if you look down at the very bottom of Maslow's hierarchy of needs in the red, these are the physiological needs, you know, having shelter and food and things like that. But you know, and as we move up, I don't know that any of us necessarily get to the top there, but when we go to the orange and the yellow, you know, what we're dealing with is with things that bring socioeconomics and other specialties or disciplines into play, and so. And we can't achieve those without that. And so a good example of that, you know, you can't read that on the bottom right, but I'll get into that in a little bit. And that's really the motivation for one of our studies. And so we use that, so that societal impact, you know, for those of you, right, you know, I think most people have probably written some NSF proposals, but if you haven't, you know, when you're writing that, that societal, that you know, Joy was talking about, the societal impact or need. And I know, you know, many of you review proposals, certainly the senior faculty here. You know, when we review them, I mean, it has to make that case right off the bat. Otherwise, you know, the reader's going to lose interest. And so there has to be a motivation, and it has to be societal. It can't be that, oh, no one's ever solved, no one's ever figured out this particular hysteretic connection. Well, you have to tell why that's needed. Okay, so let me jump to PPD 21. You know, and you know, once a presidential policy directive goes into place, the funding flows. The funding follows the presidential policy directives because the agencies follow that, and they direct NIST, they direct NSF, USDA, you name it. They're the ones. You know, the White House is essentially directing that and assigning where the funds will flow. So for this one, back in 2013, this was the Obama administration, obviously, and this was to PPD 21. You know, just it was essentially establishing resilience as a priority for the U.S. And this was primarily infrastructure resilience. And so if you look, you know, DHS, Department of Homeland Security, defines, I think, 16 or 18, I should know, but I don't remember, 16 or 18 different different critical infrastructure. But to have those then support effectively communities or community resilience. And so the big takeaway, these are the three big takeaways that I pulled from it. It's of course, 3 or 4 pages long, but so community resilience itself, it started actually in ecology. There was a landmark 1973 paper by Halling that talked about ecological resilience. And then it moved into social science and planners, urban planners, and then into economics, and then engineering. We were really late to the party. We were back, in the early 2000s in Buffalo and then some other places. But the key is that there's no one discipline that can enable the resilience of communities. So it has to be essentially an interdisciplinary endeavor, as I mentioned. Okay, so these are the stages of resilience. This is something that was developed in collaboration with us by Terry McAllister at NIST, who directs their community resilience program. And so if you look at this, you can think of your functionality, whatever that's going to be. It could be a particular physical infrastructure. It could be, that somebody has health care or can get to their dialysis appointment. It could be all sorts of things. You need roads to get them there. You need vehicles. You need, the buildings. And so that's our current state. And then damage, and I think everybody's seen this plot. It drops. And then the question is, how far does it drop? That's mitigation. And then how fast can you pick it up? And that's resilience. And what's your slope, and and do you go above, or do you go below, or do you go right back to where you started? So in 2013, we did a project here at San Diego called NEES-Soft. The full title was Seismic Risk Reduction for Soft Story Wood Frame Buildings. And the motivation for that was actually, it was a social science motivation. The motivation for a study that was done, it was called a CAP study, the Community Action Plan for Seismic Safety. And that was, the city of San Francisco didn't want their population leaving. They liked the way their city had developed, how things had grown out. They liked their historic buildings, like many cities. But they did a study and they found that somewhere between 43 and 80% of their wood frame buildings, these generally 4-story buildings, would be deemed unsafe after a magnitude 7.2 earthquake on the Hayward Fault. And I can't remember the probability. I don't know if there's any geotechs here, but it was something like a 40% chance in the next 35 years or 50 years that they would have something like this. And so, and that 25% of these buildings would collapse. So not only would there be a huge number of fatalities, thousands of these buildings, I think 5,000, 4,000, 5,000, 6,000 of these throughout the city of the Bay Area. And but they also didn't want population dislocation, because most of these are rental units. And so renters, population dislocation is a function of tenure status. And so people that are renting, they leave, or they're asked to leave. And so, and that's the community resilience aspect, is understanding something like that. And so that can serve as your motivation, and then you can still do a structural engineering project, but that motivation has to be, well articulated, like you guys know. So there was an ATC project that resulted in a document called FEMA P807, and this was to develop seismic retrofit requirements. So they didn't necessarily tell you where to put, additional moment frames or shear walls, but they told you what, essentially what, it was almost like a system ID problem. What's your hysteresis, or what's your stiffness and your strength and your distance from your center of mass to your center of rigidity needed to be. You had to reduce it because you were getting torsion. And so it did all these things, and it did it, through millions of simulations. And so what we did is we put together a 5-university project while that study was going on. And this was NSF collaboration. Again, going back to what Jose was just talking about, we had a number of industry partners. You know, we probably got, you know, thinking of the presentations over the last day. I mean, we probably had, I think we had about 1.4 million from NSF. And then, but of course, by the time we finished the project, it was a few million, it was millions of dollars. And so, so it was, you know, I never actually added it up like Tara did yesterday, I think on a slide, but yeah, I didn't dare do that. So, so congratulations on adding it. But, and so, so the idea was to develop a better understanding of soft story wood frame buildings through numerical analysis and experimental testing. And one of the things that we were able to do, that there was actually testing at Buffalo for that. We did some testing at Colorado State as well on our smaller uniaxial shake table. And one of the things that was a little bit unique about that project is, I'm not going to talk about this today, but at Buffalo, back when it was a NEES site, we simulated, we basically tested the top stories of the buildings, and then the numerical substructure for a hybrid test was the bottom story with the retrofits. And the idea originally was to actually use that to inform the UCSD test. The schedules didn't quite align due to availability, and so we wound up doing those concurrently. So I was flying back and forth from San Diego to Buffalo for a few months, which I liked the San Diego weather better, just for the record. So. Okay, so this was the life cycle of the test building. I'm not going to go through each. I'm not going to present each one, but I'll talk about them here briefly. So of course, we had construction. We got ready for testing. We did do cross-laminated timber rocking walls. They weren't designed to rock like the ones I'll show you for the 2-story and the 10-story test on another project, but they did rock, but they weren't post-tensioned, I guess you could say. But and so this was done using that by applying the FEMA P807 software to determine what the retrofit should be. So there were walls that were taking shear in line in the direction of motion, and then we had transverse walls that were reducing the torsional effect, and that was done exactly per P807. And so within this project, essentially we had, and then this was a steel special moment frame that was also designed using the FEMA P807 approach, and the idea was that we had something that, you know, was practical, it was for designers, but then we had a performance-based seismic retrofit method that we developed as part of the project, and that was the NSF style, you know, take some work from the early 80s that Anil Chopra developed, and then extend it to include torsion and things like that. And then we also looked at dampers using a performance-based seismic retrofit, and these were Taylor device dampers. Probably the smallest they've ever made, because of course wood's light. But and then we did a collapse test, and so that's the one that I'll show you today. We pulled out all the retrofits. Now the main reason, at least for wood, and I think it's the same for most structures, the main reason for a site like San Diego is you can test whole buildings, and particularly with wood, because there's so many other components and little parts that, you know, you put everything together. And, you know, we know exactly how to, you know, what a shear wall does. We can model that. We can model all these components, and then we put them together, and our system model doesn't predict it very accurately because there's too many things that are, you know, too many interactions and things going on. And so I've made the argument on multiple proposals that we have been awarded that we need whole building tests. And then recycling and disposal. And I heard that talked about yesterday, and they did it in a day actually, and that included taking all the steel out, so it was fast. That was Casper, yeah. Yeah, and I think they didn't damage anything of yours too, so. So some quick construction photos, just kind of going up. And we did do a little prefab. You can see like the let's say, I guess that's a wall, or yeah, it's a wall on the left. we prefabbed some sections of floor and then connected them. So it went up pretty fast, a few weeks. And it was, and so these are these are some buildings, you know, the typical building. They tend to be, you know, anywhere from 10 to 14,000 square feet. So they have multiple apartments in them. So when I say there's, you know, 4,000 to 6,000 of these in the Bay Area, you know, each one has between, you know, 8 and 20 apartments with, you know, a couple or family in them. So it's a lot of people. And this is what we looked like. So not exact, but it's the best we could do anyway. Okay, so so the retrofits, they all worked as they were supposed to. I'm not going to talk a lot about that because I want to get through everything today and get to some community resilience aspects. But the collapse testing, what we did is we removed 97% of the instrumentation. 3% was sacrificial, meaning you know, like Tara said yesterday, we wrote a check to whoever, I don't remember who, probably Robert as well. And so the collapse motion, we had to pick what the collapse motion was going to be. And so if you look at this, we had been testing primarily Cape Mendocino and Loma Prieta, and you know, we took a look, and they were good motions, and Loma Prieta was the one that had affected the Bay Area, of course, in 1989, and a lot of these buildings were rendered had to be demolished or very serious repairs, and of course, you know, believe it or not, even though it collapsed a freeway, it you know, wasn't that large a motion compared to, say, a 7.2 on the Hayward fault. And so so we looked at these, and if you look on the right, I guess the one right in the middle, scaled to 1.8 G spectral acceleration. That's the you can see, okay, our building period, retrofitted, it was around 0.5 seconds. Unretrofitted, it was about 1 second for a 4-story building. That's how soft these are. And so so looking at that, you look and you'd say, okay, at 1 second, they all kind of intersect right there. So who cares, right? So, but then if you take a look at the spectral displacement, you can see that the choice is clear. It's superstition hills, because what's going to happen is if you start at 1 second, we're going to elongate that period probably 2 or more seconds, and it's going to just climb right up that. And so the big thing, I learned this from the Japanese researchers over the years, going to Japan and participating on testing over there. They've done a lot of collapse tests at E-Defense, and lack of strength and stiffness doesn't collapse buildings. Can, but what collapses buildings is geometry. It's basically pulling the rug out from underneath it. Okay, so this is our shake. This is Superstition Hills at MCE. And there's not a lot of stiffness on that first story. All the retrofits are out. That's the undergraduate student enjoying himself videoing. So yeah, sorry about him. Okay, so we're at about that was Gabriel. So we're at a he did go on yeah. So Gabriel, that was Gabriel yelling, and he did go on to graduate school. So so it worked. But so we're actually close to about, it settled at about 15 point something, but it's actually it went to 17% interstory lift at that first level. And the top levels were virtually rigid. Now, the interesting thing is those top 3 levels are the top 3 stories are actually far below code, but the bottom story is so far below, it's so soft that this is what you get. Okay, so I would encourage you guys, once you've done this, I would encourage you then to do what we did. We shook it again. And here we go. And I do want to bring your attention to, let me see. And we're sitting right behind. Yeah, it's in my office. You can have it. It's a little bit. All right. So this was meant to be this. But then they did move out for this. So so this is that camera looking in, and then you can see. Let's see. Sorry, I keep trying to use the mouse. Pretty far away. And so this is the same. All right, so that's what happened to your camera. So this is so essentially what was a 4-story building is and it would have it fell to the front where the garages were, so it would have probably fallen into the street and blocked the street. So now we're kind of coming back to, like that. But not to mention, even just happening to 10% of the buildings, you're talking about, 400 to 600 of these buildings becoming uninhabitable, and they're predicting more like half of those. So you're talking about, on the order of, 100,000 people, renters. So these are all the people that, a lot of them, they have jobs across the community. They provide, services as well as interact. Okay, so now, so what you saw is a building that is not, it doesn't perform well, it doesn't satisfy the objectives of society or the goals of a community. So now I want to fast forward. This is the project you've been hearing a little bit about. I think there was a poster out front from my colleague, Shaleng Pei, who's leading this. Lehigh is doing some testing. You saw that yesterday, Jim presented as well on the same project. And those are all, there's 6 universities. So for 6 universities, to give you kind of an idea, we requested, there were different budgets. Some were 200,000, some were 4, but in the end, I think it was about 1.5 million. 6 universities went in as a collaborative project. And then we are fundraising and leveraging to try and, essentially close the budget gap for the test that I'll describe here. But before I do that, just a little bit of, and so these slides, Shaleng Pei at Colorado School of Mines had developed these slides some time ago. But so he's showing a code compliant building that's in very bad shape after an earthquake, and that does happen. To give you an idea, mass timber, or in this case, cross-laminated timber, it's essentially just these large layers of wood. I think Jim described it yesterday, so I'll skip that. But the research started in Slovenia and Macedonia, and then it moved into Italy. They did a 7-story test, or 6.5, I think, at E-Defense in Japan, and then there was some Canadian research, FP Innovations in Vancouver. And then we worked on a FEMA P695 process. In fact, I was just a couple weeks ago we just passed the ballot just passed for the Provisions Update Committee of the Building Seismic Safety Council in San Francisco a few weeks ago. So we just have a few more votes, and then it goes to ASC 7. So hopefully you'll see cross-laminated timber. You'll see tables, if all goes well, in the next version of ASC 7 they're not fancy rocking walls. They're not things like I'm going to show you today, but it's more the bread and butter, build a hotel. You can go up to essentially 65 feet. And then in Japan, Hiroshi Soda, our colleague, has been doing a lot of work with and one thing he said, we were in Hawaii at a meeting a few months ago or last summer, and one thing he said, I've been trying to collapse cross-laminated timber buildings for 3 years now, and I can't get it to collapse. And that's because of both the gravity system and the lateral system. And then like about the one work, and that actually came from the press project. That was a former team that worked on the press project here in San Diego back many years ago, and he took that the concrete technology to wood, and that's how that project started. And then we had a beginning grant with Ling or Chilling Pay leading, and then we did a test here a few years ago, and so I'll talk a little bit about that. This is the team. I won't go through it, but you can probably see it. It's kind of small. I don't know what happened to this. And that's the key. You can't test a full building without that. So to give you an idea of the project, so we did the 2-story test. There's testing at Lehigh. I think that's going to bleed right into January 2020. And then validation test. That's a collapse test, right, Joel? Are we doing a collapse test on the 10-story? Unless something goes terribly wrong. So this was the specimen. So you can see we're going to shake this direction. So you can see we're actually quite a bit larger. This was 50-some feet, I think 54 feet. And so we're taking advantage of the fact that wood is light, and so this whole building, about 160, 170 kips. And so these are post-tension rocking walls. You can see the post-tension rods here. Jose had mentioned the U-shaped clips there. And I think I was going to try and get both these to play, but I don't think I can, right, Robert? So I'm going to just hit them both, and then, oh, it worked. Okay. And that's, I believe that is Northridge Canoga Park. And we're running the same record twice. Yeah, you can almost guess the period of the building, can't you, just hearing that? So, exactly. Okay, and then here's another one. So the other one started, Robert, the other one started by itself. Should I just click and click it? Okay. Okay, same test. So, um, and one thing I would say is don't underestimate the number of bodies you need on site. More people, don't ever refuse anybody unless it's troublemaker. Otherwise, invite them. So I'll jump past here. So this is the 10-story system level validation. This gives you kind of an idea. As you can see, we have the but it's a feeling from the street. So the idea is it'll be the first building made out of concrete that minimizes downtime, and the method on that is to do this with the community goals in mind. So how do you actually de-aggregate the goals of the community into the performance of a single building? That's what we're to do. And then this was developed by Lang. So so the music is for you guys. I'm not sure where you got it, but oh, do we have the music? Maybe not. Probably better. It's not blending. So this the size. And there's our upstairs right now. No, we could talk a lot about that. Decided that it probably could be too much to figure out. Also, if we have an elevator, it can't really my weight loss plan. And so this, so you can see it'll be, we're also considering, in talking to MK, we've been talking to MK, Seattle and some others, and so we're doing some fundraising. So we may have some diaphragms that are nail in under mechanical fasteners. Sometimes you have to, at least with these big projects, we've always had, sometimes you have to make concessions and include something that you didn't originally write in, and you just make sure that it works with your, it works with your objective. You don't want to take a scrimp on any of those. So, no, this was it. Okay. Well, I won't show you the whole thing, but. And if the music's not making you smile. All right, I'll go ahead and jump past since we've seen it. But so I mean, like completely over. And then 2021, we'll be doing some staging in the spring, starting construction, and then summer is the shake table test. And excuse me, I forgot this part. So probably the most important part is
not every Friday, but almost for 2 minutes, 5 minutes almost every Friday. And then we're on a level. But if you're interested in doing a payload, you have to involve word. You know, it's something that you know, it can be leading that, and so if you know that and you catch it, you know, it's something that, you know, there's a chance. So if you talk to us, they could go in and because it will be the tallest building ever tested on a cake.
So how tall was the wind turbine? Oh, so we have to go 101. Okay. Okay, and then I want to acknowledge, so you can see all and then a lot of donations. The NARI at UCSD staff always. Okay, so I want to circle back around. Let's see, I think I have a few minutes left. So I want to circle back around to back to resilience now. So you saw a system that performed poorly and wouldn't satisfy the goals of a community or an urban of a city, and then you saw one that likely would, you know, assuming that the 10-story will behave like the 2-story model did. And to give you an idea, that 2-story building, we let's see, I believe by the time just for that phase, I think we ran 23 earthquakes and more than half of them at MCE. And when we removed it, there was virtually no damage. So so that's to give you an idea. So that we didn't take it past about 5.5%, but could have, I think. So as I mentioned, 1 and 2, those deal with risk primarily, and then our phases or stages 3 to 5 focus on resilience. So resilience is about getting your community back long term, and to do that, you know, buildings are well-performing buildings are necessary. They're a necessary condition, they need to be there, but they won't do it by themselves. So to give you an idea of, you know, within the NIST Center for Community Resilience Planning, we're in the process of renewal review. So we hope to have another 5 years starting on February 1. We'll know here in a few days, I think, actually. And to give you an idea, these are some of the things that, you know, that are going on. But these are all areas, even though they're being worked on, there's huge gaps in all of these. You know, and you know, for example, you know, earthquakes and tsunamis, you know, in succession. Yeah, we've looked at, you know, people in the center and others have looked at modeling the earthquake effect and then the tsunami hitting. But do we have fragility for that? No. We have some. We have a method for it, but the capacity is not there. So there's all sorts of physical infrastructure, transportation. You know, I know Joy said they don't necessarily fund some of this, but they do fund it in the context of resilience. They do fund network analysis, things like that. And so if you write it fundamentally, and not say, hey, I want to test this bridge, or I want to do this. You write it fundamentally and treat it as a basic research problem, and then make the example application something like that. You know, they definitely will review it. You know, water and wastewater, predicting, you know, physical damage. So this is some work by Paulo Gardoni and so these are two of the networks that we're combining with the methodology design. Basically, come back when the building for the project, and the idea is to find that intersection so the building isn't the weak link to make it functional. The building repair, I should say. And so looking at electrical power networks, natural gas networks, telecommunications, and all of these things, all of these things interacting with the buildings. And then aging and deterioration, and this is, I mean, most of what we do, you guys know, most of what we do now as civil engineers is fixing messes and things that have deteriorated, or new is great, but that's not what's out there. And then one of the keys, and this is, I definitely encourage, I've been working with, this isn't engineering. Immediate loss. This is a computable general equilibrium law. Thousands of different equations, a couple of different equations that basically describe all the input and output to a community project. It's actually natural economic with developed the region. Now we've been able to reduce community size, and the bigger the community, the more accurate it is. But we've done it for Seaside, Oregon, which was only a few thousand, I think 6,000 or 10,000 people, and so it'll predict losses in production, wages, all sorts of things, and so you can see if you have a there's your societal impact. And then social science and modeling, I talked about this. Seems really quiet in here, is it because there's no videos? Social science modeling and analysis, population and employee dislocation, and these things are huge because without without a population, they'll always, you can't be resilient and be missing 20% of your population. Housing and housing restoration and recovery, business interruption is big. Small businesses can go about 2 weeks without funds, and then they're gone. And so a lot of this is based on socio demographic and socioeconomic vulnerability data. So one of the huge gaps in probably all is we have a number of recovery models, but to have them interacting, I think there's a way to bring that into like a broader project to end us out. That's something that project that was a big a lot was developed. But for recovery, the key is you don't want it to just be engineering recovery, because just like a building, you can't do any work until you get the permit. You can't do any work until you clear the debris. So there's a lot of things that aren't engineered. And then optimization and decision making, that's and so this involves not just optimization for direct economic impact and optimization for long-term impact that's computed from the CGE model. So that's the idea of these things. So I'm going to wrap up here in just a moment. Hopefully we can take a question or two, but so just to give you an idea, this is the center. I just wanted to, and we're working on all of that, but there's way more work than we'll ever be able to do. And so it's a 12 university partnership with the National Center for Supercomputing Applications, and we've been talking with the Sim Center, trying to figure out some, with the NERI Sim Center, trying to figure out where those commonalities are, so that we can, and we'll probably put on some data workshops with Design Safe CI and things like that. And so we're starting to do that. We just had a call about a month ago. And these are the 3 thrusts within the center. And then what I'm going to do is, Joel, I think I'm kind of out of time, so I'll just wrap up in 2 minutes here. But so we do have a number of test beds, and these test beds, 2 are going to be available on Friday, and we'll be releasing open source software. It's in Python, so you do have to code in Python, or your students do, not you guys. But And that's called InCore. Seaside, Oregon will be one of those releases. So that'll be an example. There'll be a Jupyter notebook that will be an example for that. And there's MMSA, which is a big one, and then Galveston. And then the Joplin tornado will be the other one. Okay, so to close, I want to come hopefully full circle back to the Stafford Disaster Relief and Emergency Assistance Act, or the Stafford Act as it's known. Many of you, some of you may be familiar with this, but last year the Disaster Recovery Reform Act was passed. Essentially it authorizes, the pre-disaster mitigation funds. And this is through, if you look at the bottom there, this is through the Building Resilient Infrastructure in Communities, or BRIC. And did anybody know that was passed? Yeah, so, well, I did, but as there's disasters and funds start to flow. And so with that, again, I just want to underscore that creating resilient communities is a multidisciplinary endeavor. Buildings, lifelines, social institutions, economics, and then governance is key. And governance is hard. It's very hard to model. I'm not sure how. So with that, I want to say thank you, acknowledge NIST for the funding of the center, and also thank Joelle and all the UCSD colleagues for their hospitality while I was here for a day. And that's the NEES-Soft acknowledgements. You can see the number of partners. And then finally, on Friday, we'll release InCore, and you can email us there or follow me on Twitter, and I will announce the release on Friday of that package. And lastly, sorry, this is a Lifelines conference down at up at UCLA, led by Craig Davis. I think most of you know Craig. So, and that'll be in 2021. So February, it's the 50th anniversary of the San Fernando earthquake. And it's primarily lifelines with interaction to buildings. Thank you.